Hi everyone! In this video I will be discussing my findings from Lab 4, Oscillations. So in this lab we will aim to observe the motion of an oscillating and swinging spring, record the data points obtained from the motion, and simulate the motion through a computer model, and compare real-world and hypothetical motion. Throughout this lab we will use these fundamental principles. We will use the velocity and position update formulas to calculate kinetic, gravitational potential, spring potential, and total energy. We will also need to calculate the force of gravity, the spring force, and the net force. So in the pre-recorded video given to us, it shows the spring in motion. We see that it is moving up and down and side to side, so it has motion in the X and Y directions. So for our code, we change the initial conditions. We update our mass, the initial position, and the initial velocity. I calculated the spring constant by rearranging the period of oscillation equation. The equation is 2 pi times the square root of m over k, so we rearrange this to get k equals 4 pi squared times m over t. T represents the period of oscillation, and at this point t is still unknown, so we find it by dividing a time interval by the amount of periods that have passed during this interval. We look to our y graph to calculate t, and thus our spring constant, since the spring has predominantly downward motion. We get t equals 1.524, so plugging that and 0.402 in for m tells us that our spring constant is 6.83. We find the relaxed length of the spring by setting the weight force equal to the spring force. We find that the relaxed length is 0.123. We can find the non-relaxed length of the spring by subtracting the spring position from the ball position. We find L hat by dividing L by the magnitude of L, and we find S, the stretch, by subtracting our relaxed length from our non-relaxed length. We update our energy formulas using the principles previously shown. We continue to update our fundamental formulas. We calculate our energy changes, and we run the code. So we have a model simulating the spring and the weight's motion. This graph shows the actual motion of the spring in red and the computer prediction in blue. Oftentimes with real-world versus computer-simulated models, the two are never exactly the same. In this case, the discrepancy is due to real-world forces such as drag limiting the system's movement, but as the estimate is never more than 0.02 meters off, this is a pretty good prediction. In this graph, we see our different energies. We see the amplitudes of the kinetic and the spring potential energy vary. This is because when the spring is in different points in its motion, the kinetic or the spring potential energy will increase or decrease. The amplitude of the gravitational potential energy stays the same because gravity is a constant force. The change in total energy does not fluctuate at all due to the law of conservation of energy. Energy can exist in different forms, but it cannot be destroyed. So the lab asks if the energy principle is satisfied. The answer is yes, the energy principle is satisfied because it states that the change in energy equals the energy input from the surroundings. There are no surroundings since our system is made up of the spring, the weight, and the earth, so if there are no surroundings, then there is no energy input to be had. No energy input means no change in energy, which is seen in the graph. Here we see the graphs representing the motions in different directions. When the video starts, the spring's x position is negative 0.117 meters, and the y position is negative 0.638 meters. These differences in position explain why our two graphs have different periods. The period of oscillation for y is 1.524, and for x is 1.81, so y moves quicker. The motion of x depends on gravity, since side-to-side movement would not be possible without gravity, and the motion of y depends on the mass and stiffness of the spring, since a vertical spring will oscillate with the same frequency with or without gravity.